Myself Pushkal Kumar Shukla, Assistant Professor in Computer Science Department at Akgec Engineering College, Ghaziabad. Today, I will discuss a topic finite automata with outputs. This topic is useful for the BTech 4th semester students. Finite automata with outputs. Objective of this topic is to make the students able to understand the requirement of finite automata with outputs. Implement Mealy and Murray machine and convert Mealy machine to Murray machine and Murray machine to Mealy machine. Finite automata, as discussed so far, have a limited capabilities. A finite automata, as the name suggests, finite automata, basically we are talking here non-deterministic finite automata and deterministic finite automata. As the name suggests, deterministic finite automata, it means the number of states are finite and the input alphabets are finite, and it is a fix for a particular state and a particular input. It goes to the fixed state, so that's why it is a deterministic. That's why it is called a deterministic finite automata. And non-deterministic and finite automata, for a particular state and particular input, the next state is not deterministic actually. It is non-deterministic. It's not fixed. So that's why it is known as non-deterministic finite automata. So finite automata, DFA and NFA, having a limited capability. It means accepting or rejecting a string. So finite automata with outputs do not have a final state. But in the case of NFA and DFA, we have seen there is a final states for accepting or rejecting the strings. But in the case of finite automata with the outputs, do not have a final state. Finite automata with the outputs of two types, here a Mealy machine and a Murray machine. Basically, this type of finite automata producing outputs. So that's why one is a Mealy machine and second one is a Murray machine. So Mealy machine, what is a Mealy machine? In a Mealy machine, the output is associated with transition. It means the output depends on the present state and the present input. In case of a Mealy machine, the output is associated with the present state and the present input. While in a case of a Murray machine, the output is associated only with the present state. So there is a difference in output. So lambda here is the output, and it is a mapping from Q into input alphabet, that is sigma, to delta. It means that output function is associated with the present state and the present input. But in the case of Murray machine, the output depends only on the present state. So here lambda output function is associated with the present state. Here this is the present state. So this is a difference in transition function. So mathematically, a Mealy machine is described as 6 tuples. 6 tuples are there. That is Q, sigma, delta, this is lambda, Q naught, and this is delta. So this is Q is a finite non-empty set of states. Q is finite non-empty set of states. This is a sigma. Sigma is a set of input alphabets. This is set of output alphabets. Delta is a transition function mapping from Q to sigma to Q. And lambda is the output function mapping from Q to sigma to delta. And Q naught is the initial state. Q naught is the initial state. Example of Mealy machine. Mealy machine, suppose we have to design a Mealy machine that accepts all strings over sigma equal to AB, ending in AA or BE, BB. Yani ki it means कि this machine accepts all strings over AB ending in AA, like BAA. So this type of Mealy machine will accept like BAA, BAAAA, this type of string. Yeah, ending with BB, yani BB. Yeah, ending with AA. Yeah, B B A B B. Yeah, A B B. Like this type of string is going to be accepted by the Mealy machine. So how we will design it? So we start from the Q naught state. If it, this is the state Q naught, that is the element of Q. This is the input. This is the input symbol, and this is the output symbol. So in a Mealy machine, input and output is there. So this is input A. So Q naught after on the state Q naught, if taking input as A, it produces output 0 and next reaches to the Q2. And at Q2 state, after scanning input A, it produces the output 1. Similarly, at Q2, it goes to the Q1 state after reading input A, B and produces output 0. And similarly, at the state of Q naught, after taking input B, it produces output 0 and go to the Q1 state. And at the Q1 state, after taking input A, it produces output 0 and go to the Q2 state. And by this way, we are implementing either ending in AA or BB. So a Mealy machine that accepts either ending with the AA or BB. So here we can write this transition diagram through the present state. To the present state, Q0, Q1, Q2. 3 states are there, Q0, Q1 and Q2. And after taking input A, it goes to the state Q2 and produce the output 0. So write in a transition table like this. So how we will write? After at the state Q0, after taking input A, it goes to the state Q2 and produce output 0. So this is a state and this is next state actually. This is a next state and this is the output. Again, this is a next state and this is output. Again we see at state Q1, it goes to the Q2 at reading input A and produce output 0. So Q1 after reading input A goes to Q2 and produce output 0. Similarly, at the state Q1, after reading B, it goes to Q1 and produce output 1. So make this transition diagram, and with the help of this transition diagram, we can make it a transition table. So this is a Mealy machine. So Mealy machine output is associated with present state and the present input. While in the case of Murray machine, the output is associated with only the present state. So Murray machine is described as usual by a 6 tuples. 6 tuples as mentioned in a Mealy machine. There is only difference in the output function that is associated with Q2 delta. Create a Murray machine that counts number of A mod 3. So A mod 3, a Murray machine we have to design A mod 3. It means ki suppose A. So A 3 times of A mod 3 will give a remainder 0. So output will be 0. So in case of A mod 3, it will give our output 1, and A mod 3, it will give a remainder 2. So 3 types of outputs are there, 0, 1, 2. So 0, 1 and 2, 3 outputs are there. So Q0 at the state Q0, if it reads B, then it goes to the Q naught state, because B mod 3. So here number of A is 0 and 0 mod 3 is a 0. So output will be 0. So here the output will be 0. So after reading at the state Q naught, after reading B, it will go to the state Q naught and output is associated with 0. Again we see reading with BA. Suppose string is BA, so number of A here is 1 and 1 mod 3 will give you a remainder 1. So it will go to the state Q1 and output is associated with 1. So after reading A, it will give you output 1 and state is going to change from Q0 to Q1. Again, by taking example AA, suppose we will take a string AA. So AA mod 3 will give you a remainder 2. So remainder 2, a number of A's is 2 and 2 mod 3 equal to 2 will give you output 2. So here we see AA, it will give you output 2 and state is going to change from the Q1 to Q2. So this concept is going to use to design the Murray machine counting number of A mod 3 by this way. Again, if you take AAA, so AAA number of A's here is 3 and 3 mod 3 equal to 0, so it will reach to the output 0 at Q0 state. So here we see Q0 state associated with the output 0 and Q1 state associated with the output 1 and Q2 is associated with the output 2. So by this way we can make a Murray machine. So how to write this in the tabular form? So present state Q0, Q1 and Q2 are there, Q0, Q1, Q2 are there, and the input A, corresponding to input A, it goes to the Q1, so Q1 right, corresponding to B, it goes to the Q0, and Q0 corresponding to Q0, present state, the output is 0. Here we see state is Q1 and after taking as a input A, it goes to the Q2, taking input as A, go to the next state Q2, and after taking B input, it goes to the Q1, and the corresponding to Q1 state, the output is 1. The output is 1. Here we see for the state Q2, Q2 after taking input A, it goes to the Q0. So after taking input A, it goes to the Q0. And after taking input B, it goes to the Q2 and corresponding to this Q2, the output is 2. So output is 2. So by this way, we can represent in the tabular form, transition table. Now, the question is how to convert a Mealy machine to Murray machine. See with the examples. So this is the Mealy machine. This is the present state Q0, Q1, Q2 and Q3 are the present state, and the next state on input A, the next state is Q3, Q0, Q2, Q1 and correspondingly the output is 0, 1, 1, 0, and after taking input as a B, the next state will be Q1, Q3, Q2 and Q0 and the output associated with 1, 0, 0, 1. So to convert into the Murray machine, here we will see the corresponding to Q0, the output is 1. Corresponding to Q1, the output is 1 and 0. So here corresponding to state Q1, two outputs are there, 0 and 1. So split Q1 into the two states, Q1 0 and Q1 1. Corresponding to 0, the state Q1, and output is 0 and the Q1 state and output is 1. So Q1 split into the two parts Q1 0 and Q1 because corresponding to Q1 two output is associated 0 and 1, so split into the two states Q1 0 and Q1 1. Similarly, Q2 corresponding to Q2 output is 1 and again we see output is 0, so split again Q2 into the two parts Q2 0 and Q2 1. So write this present state Q0 is here, Q1 Q1 is divided into two parts, Q1 0 and Q1 1. So Q1 0 and Q1 1, two parts are there. Again we see Q2 is divided into two, Q2 0 and Q2 1. So again we write Q2 here in the place of Q2, two states are there, Q2 0 and Q2 1. And next Q3, then write Q3 here. We write next state, that is on taking input A, the states is Q3, right here Q3, Q1 that is Q0, so right here Q0. Again Q1 is divided into the two parts, Q1 0 and Q1 1. So corresponding to this, the output next state is Q0. So right in both places next state is Q0. Again we see here Q2 is divided into the two parts, split into the two parts, Q2 0 and Q2 1, and corresponding to Q2, the next stage is Q2. So this is, and output associated is 1, so write here a Q2 1 and Q2 1. Q3, that is right here Q1 0, because Q1 is there and 0, so corresponding to Q1 0, we write state Q1 0. In the same fashion, we write here Q0, Q1, and output is 1, so write in this place Q1 1. Here state is Q3, so Q3 is alone, so write here a Q3, and write in two places Q3, because Q1 is split into the two parts, this, so write in both places Q3. Then Q2 0, so write here Q2 0, Q2, and corresponding to it the output is 0, so write here Q2 0 in both places, and then Q0. So by this way we convert this into the Moore machine. So here see the transition states in this is a 4, and in this the states are like 6. So it will take a more space as compared to the Mealy machine. So Moore machine will take a more space as compared to the less, because the number of states here is 6 and here number of states are the 4. So by this way we convert a Mealy machine to the Moore machine. Conversion from Moore machine to the Mealy machine. For understanding the conversion of Moore machine to the Mealy machine, let us take an example. Suppose the Moore machine transition table is here. Moore machine, the output is associated with the present state. In a Moore machine, the output is associated with the present state. So here we see the P is associated with 0, Q is associated with output 1, R is associated with 0, and S is associated with the 0. So here we see the output is associated with the present state. So this is the output and associated with the present state. So in a Mealy machine, we have to write present state in the same way, present state, and this is the next state, and input is A and output is B. Again we make it as a here state, this is a state and corresponding to it output, and again we make here in two parts like state, and here we write output. So in the previous here see P is associated with 0. So here we see P is associated with 0, Q is associated with 1 output, R is associated with 0, and S is associated with 0. So we will write here a state S corresponding output is 0. So write here as 0. Q is associated with output 1, R is associated with output 0, and S is associated with the 0. Q is associated with the 1, R is associated with 0, S is associated with 0, and P is associated with 0. So this is a Mealy machine. So we convert here a Moore machine to the Mealy machine. So this is actually 0 1 0 0. This is what 0 1 0 0 and 1 0 0 0. So this is a 1 0 0 0. So by this way we convert it. By this way we convert it. So here we see a conversion from Moore machine to Mealy machine and a Mealy machine to a Moore machine. So difference between a Mealy and a Moore machine. So if we're talking about difference, so basis of comparison, that is description. A Mealy machine change its output based on its current input and the present state. So here we see a Mealy machine, the output is associated with the present state and the present input, present state and the current input. Output is placed on the transition. While in a case of a Moore machine, output of a Moore machine depends only on the present state, current state, and not on the current input. Output function is a mapping from this to this, and output here is a function of this to this. This part is not there in that place. So this is a mapping from present state and the present input, and there is only a present state, and this is the output. Actually, output. A counter is not a Mealy machine. A counter is a Moore machine. Design not necessarily easy to design. Mealy machine is not necessarily easy to design, and Moore machine it is easy to design. It produces n length outputs, strings corresponding to the n length input string. But in a case of Moore machine, it produces n plus 1 length outputs string corresponding to the n length input string. So this is the difference between the Mealy machine and the Moore machine. Now come on the minimization of DFA. So minimization of DFA, so what we will do here, this is a very important topic that is frequently asked in AKTU examination. If you're talking about the minimization of DFA, so first, it refers to the removal of those states of DFA which presence or absence in a DFA does not affect the language accepted by the automata. So minimization of DFA refers to the removal of those states of DFA which presence or absence in a DFA does not affect the language accepted by the automata. The states that can be eliminated from automata are unreachable or inaccessible states, dead states, non-distinguishable or indistinguishable states, or equivalent states. So these type of states can be eliminated from the automata because their presence does not affect the language accepted by the automata. How to remove this? Now the question is, so this is a transition diagram of this DFA in which we have to find which states are indistinguishable states, which are inaccessible states, and which are unreachable states. So identify this. There are so many techniques. One technique is a May-Helnorud theorem. The second technique is to finding out the equivalence pi naught, pi 1, pi 2, pi 3. And third technique is removal of like unreachable states directly from the DFA, inaccessible states like that. And by this way we can eliminate this. Thank you.